hopefully a little bit of review. This is ratios and proportions, which we've seen before. Starting off with just some vocab. A ratio is when we have just one fraction. It's a comparison of two different quantities. So for example, A over B, we can also write it as A to B with a colon in the middle. We have fractional notation is this one. It'll ask you to use fractional notation in your math lab later today, so that's the one. Otherwise, I don't remember what they call the other one, but you might have to use both. Then we have a proportion. A proportion is different from a ratio. A proportion is when we take two ratios and we set them equal to each other. So most notably, there's an equal sign in the middle. It is two different ratios. We use these to solve problems where we are finding missing information. We'll set together a proportion. We also have extended proportions, which are just proportions that we make longer by adding more stuff to them, but still a bunch of ratios and equal signs. We'll see scale drawings. We'll see scale. Scale is going to be an important part of our proportion writing. A lot of the times when we set up two ratios in a proportion, one of those ratios will be the scale. And then lastly, when we have a proportion, we're going to solve that proportion by cross multiplying, using the cross product property. So that's like multiplying in an X shape. It's different than when we multiply two fractions together. Multiplying two fractions, we multiply the top row and the bottom row. However, when they're separated by that equal sign, we should be multiplying them in an X pattern instead. Questions on that vocab? Hopefully we've seen this stuff before, so it's not new. What is maybe new for us is this box right here. This is properties of proportions. I don't think this is something you necessarily need to have memorized, but it is useful to have all of these things in your back pocket. I'm going to color code this just a little bit. So if I have this fraction, A over B equals C over D. So say you write this proportion. You're doing a word problem. This is what your proportion ends up looking like. The person next to you could write any of these four proportions here and still be equivalent to the proportion that you wrote. So their answer is still going to be the same as your answer because all of these different versions of these proportions are equivalent. The most common one that we see is this first one, because this first one is just the cross product. This is what we get when we cross multiply these two fractions. So say I multiplied them like this, I would be multiplying A times D and B times C to get my cross product. That's just the result of cross multiplying there. Nothing crazy. The next two of them are kind of intuitive. They're basically saying as long as things kind of still line up the way that they were originally, we can swap things and we can flip things around. So if I take a look at number 2, what happened here is we took the numerators of my two fractions and we put them at the bottom, and then we took the denominators and we put them on top. Okay, I would just call this flipping my fractions. We're taking the reciprocals of them, still equivalent to the originals. All I did was change where the tops and the bottoms are. Doesn't change my answer. The third one is a little bit different. Sometimes we see rotations where the entire thing rotates. Maybe that's more like number 2. But in number 3, what we did is we kept A and D where they were and flipped B and C. So I kind of see this as like a reflection of sorts, maybe a rotation. I would just call this one moving across. It's not like you need to know these names by any means. It's just how I remember them. But essentially all we did here was we took B and C and we flipped them. You could do the same thing with A and D. You could leave B and C where they are, flip A and D, whatever it is, you're still going to have an equivalent proportion. Is what I'm saying kind of making sense a little bit? Equivalent proportions. The last one is the weird one, because we see this one pop up a bunch. So I would maybe star this or circle it or whatever, because this is the one that comes up like to try to trick you sometimes. So it's really nice and easy to see here when I have variables because I can't combine those as like terms, but it's a little bit trickier to see. We'll see it later when I don't have variables and I just have like numbers that can combine. But essentially what we're doing here is we're taking the numerator and adding the denominator over the denominator. So again, this is numerator plus denominator over denominator. And I'm talking about numerators and denominators of this original proportion. Okay, so imagine for a second that you have numbers here. Instead of C plus D over D, it might look like 7 over 4, and you're trying to think of 3 plus 4 over 4. Okay, so they try to trick you just a little bit. Just keep that one in mind. Any questions on these proportions? Equivalent proportions? Okay. The rest of this should be pretty straightforward. We're finding each ratio. In numbers 1 and 2, we're just literally going to write the ratios. So in number 1, games won by the Hawks to games won by the Tigers. One thing we need to pay attention to is the order that they are saying these things. So it's saying games won by the Hawks to games won by the Tigers. That means I want to list the games won by the Hawks first, then the games won by the Tigers second. We could also write this as a fraction, 16 over 15. Both of these would be acceptable for me. In number 2, it says find the ratio of the longer side to the shorter side. We got to do a little bit of extra work here. First of all, the longer side is going to be this 40 inches. 40 is a little bit larger than 3 feet. We have to get common units in order to write our ratios. So I'm going to convert one of those to be the same as the other. The easiest one is to convert that 3 feet. 3 feet is the same as 36 inches. So when I write the ratio from my longer side to my shorter side, 40 to 36, I should keep that in that order, longer to shorter. And then I also want to reduce this. So imagine that it was a fraction, 40 over 36. All your fractions should be reduced. So we should write this as, what is it? 10 over 9. Like that. Or same thing if it's a colon. Just because it's a colon instead of a fraction doesn't mean you don't have to reduce it. This would reduce to 10 to 9. So either way you write it, your fraction should be reduced. Questions on that? Okay. In number 3, we're talking about Ashley. She conducts a survey. She wants to predict something. She wants to predict the total number of students who own cars in this population of student drivers. If we are trying to predict something or find a missing value of something, this is when we start setting up a proportion. So, when we set up a proportion, remember a proportion is when we set a ratio equal to another ratio. So we will have a fraction equal to another fraction. The important thing about proportions, again, yours might not look exactly like the person next to you because we have all of these equivalent proportions. However, as long as you are lining up the correct things, you should be okay. So take a look at this problem. It says Ashley conducted a survey of 50 student drivers and found that 28 of them owned cars. So these first 2 numbers represent like my survey population. I'm going to set that up on the first side of my proportion. There are 50 drivers and 28 owners of cars. That's her survey size. Now she's trying to predict out of the entire student body of 755 students who drive to school, how many total students own cars. So this is my X value here, how many students own cars. And I'm going to line those pieces up. So there's 755 students who drive to school. That has to line up with the 50 students who drive to school that she surveyed. The X amount of students who own cars has to line up with the 28 students who own cars in her survey. That is the most important part of the proportions. Once we get here, yours might not look the same as your neighbor's, but you can still cross multiply and get the same answer here. So 50 times x is 50x. 28 times 7, 55. 21,140. We divide by 50 to get x equals 422.8. Can we have 0.8 of a student? No, so we have to round this up. I'm going to say about 423 students own cars. Any questions on that? Okay, flip it over. Here's what I was talking about with this box on the first page. So what you're going to see is they're going to give you an original starting proportion like this. Ours is A over B equals 3 over 4. Just going to make it a little bit bigger. What they want you to do is, using that original proportion and a starting place, write the equivalent side of that proportion. So here's my original. It says, okay, we multiply 4 times A. What would be the equivalent on the other side of this equal sign? Well, 4 times A is like multiplying in an X shape. So the other side of that equal sign should look like 3B. Does that make sense, what we're doing here? We're trying to match it up. In letter B, it says A over 3. Well, here's A, and here's 3. The other side of that fraction should then be B over 4. Question? Okay. I'm going to sneeze again. Here's the weird one. A plus B over B equals blank over blank. This one's nice. They did it with the variables for you first, so you can kind of see what's going on here very clearly. It's A plus B over B. That's numerator plus denominator over denominator. So the other side should also look like numerator plus denominator over denominator. 3 plus 4 over 4. You should reduce this, or not reduce, but simplify this to 7 over 4. And that would be our answer here. Now what they're going to do to try to trick you is, instead of starting you off with A plus B over B, they're going to start you off with this 7 over 4. And then you're looking at your original equation like, what the heck, how did we get a 7? There was never a 7 to begin with. Well, you have to think numerator plus denominator over denominator gets us 7 over 4. So they'll give it to you this way and make you go backwards from here. So just keep that in mind. Any questions about this? Kind of weird. Okay. Do we think we can solve these proportions? I think that we can. Remember, solving a proportion is just multiplying in an X shape. So for this one, I'm just going to do it really fast for us. 5x times 8, 40x. 4 times 35, I don't remember off of the top of my head, 140. So x is 140 divided by 40, 3.5. Nice and easy, not trying to trick you. The tricky part is when we get to proportions that look more like this. When I do a proportion like this, the 15 times the 5 is pretty straightforward. That's 75. However, on the other side, the key thing to remember is that we're going to have to distribute here. I have to multiply that 3 to both the x and the minus 3. So this is like 3 times x minus 3 in parentheses, and to solve, we're going to have to distribute. I believe this is 28. Questions on that? Okay, I'm going to change this one a little bit for you. Let's say that it's not like this. Let's say it's x plus 5 over 7 equals 5 over x plus 3. So I'm flipping that second fraction so we can get an example of what this is going to look like, because this will pop up on your homework. Same thing. We're cross multiplying. I'm going to do 7 times 5 to get 35. That's straightforward. But when I do this other side, x plus 5 and x plus 3, I'm going to have to distribute this, double distribute. So this is 35 equals x squared plus 3x plus 5x plus 15. From here, I'm going to solve. This is going to require factoring, just a warning. So this is 0 equals x squared plus 8x plus 15 minus 35 minus 20. I don't actually know if this does factor. Oh, yeah, it should. X plus 10 and x minus 2. Your two answers here are going to be x equals negative 10, x equals positive 2. Okay, you are going to have to factor, so just be prepared for that. Questions on this? We're almost done. Number 6, the ratio of measures of the angles in a triangle is 3 to 4 to 5. Find the measures of the angles. Basically, what this is saying is I have 3 angles, and they're being like multiplied by these numbers, right? One is a multiple of 3, one is a multiple of 4, one is a multiple of 5. They're all in the same ratio, 3 to 4 to 5. Okay? We know that angles add up to 180. So this is where I'm going to start my equation. This is a weird one. Just follow along with me here. I don't know what the magic number that they have in common is. 3 times what? 4 times what? 5 times what? I don't know. So that's what I'm going to call x. I know that all 3 angles here have to add together. So 3 times whatever my magic number is, 4 plus whatever times whatever my magic number is, and 5 times whatever my magic number is. I don't know. They're in a ratio of 3 to 4 to 5, though. That's all I know. I simplify this. Is that right? And then I divide by 12. I think it's 15. Let me double check. Yes, 15. So that's saying my magic number is 15. And if I wanted to go back and figure out what these 3 angles were, let's say angle A. Angle A is 3 times that magic number, which is 45. Angle B is 4 times that number, which is 60. And angle C is 5 times that number, so 75. So these 3 angles are in a ratio of 3 to 4 to 5. Kind of weird. Any questions on how I did that or why I did that? Okay. Almost done. Number 7, here is a scale factor with a map. Whenever I'm trying to find a missing value, find the actual distance, again, we're setting up a proportion. So let's start with a fraction that equals another fraction. What I like to do here, when I have these scale drawings, scale models, whatever it is, you have some kind of scale factor, I take that scale factor and I'm going to write it into my ratio, my proportion, right away. So I'm going to do 0.5 inches to 50 miles. And I like putting those units in there because it helps me line things up. That's my scale factor. Now, they're measuring 2 cities on a map, and they measure my distance is 3.5 inches. What I'm trying to figure out is the actual distance in miles. So I don't know how many miles. I'm going to line up X miles. Again, looking how I'm lining up miles with miles. And 3.5 inches with inches there. And there's my proportion. Already set up. Again, yours might not look like your neighbor's, but that's okay. We cross multiply. 0.5x equals 175. Okay. This is like my pet peeve. When we are dividing by 0.5, I see it so often. You're like, oh, let me just divide by 2. When you see divide by 0.5, you better be multiplying by 2, not dividing by 2. That number should be getting bigger. This is 350. I see it all the time. Use your calculators. Please, you have them. If you're dividing 175 by 0.5, you're not dividing by 2, you're multiplying by 2. Questions on that? Okay. Number 8, find the actual dimensions of the bedroom based on the scale drawing. I have a length, I have a width, and I have a scale factor. I'm going to set up 2 different proportions. One for the length and one for the width. Let's start with the length. Again, I like to put in my scale factors first. So my scale factor is 1 inch to 16 feet. And then it's pretty easy to just line the rest of it up. 7/8 of an inch to I don't know how many feet. That, when I cross multiply, gives me 14 feet. Same thing over here. 5/8 of an inch to I don't know how many feet. Gives me 10 feet. Any questions on that? Okay, last one. This is kind of a weird one. I'm leading you into something here. Consider a painting on a 22-inch by 28-inch canvas. Suppose you wish to make a 1:2 scale model of the painting for art class. What is the ratio of the areas of the model painting to the actual painting? So this is saying we're taking a model, we're making it bigger, we're taking the actual one, we're making it bigger for the model. We're comparing the ratios of their areas. The ratio of their sides is 1:2. What's the ratio of their areas? Here's a hint, they're not going to be the same. Side lengths and area measures do not scale by the same factor. So let's take a moment to imagine I have 2 canvases. I have a 1x1 canvas. The area of that 1x1 canvas would be 1 square unit. If I double the side lengths of that canvas, and now I have a 2x2 canvas, my side lengths have a scale factor of 1:2. However, my new area is not going to be 2. It's going to be what? Should be 4 square units. So my areas have a ratio of 1:4. That logic should apply here with my new big canvases as well. So let's take our 22 by 28 canvas. The measure of the area of my 22 by 28 canvas is going to be 616 square inches. I'm going to make that painting 2 times as large. So now it's a 44 by 56 inch canvas. I need you to understand that you cannot take this area and double it. We have to actually go in and figure out what is the area of that canvas, 44 times 56, to get 2,464 square inches. And then from here, we can set up our ratio. I want the ratio of the areas of the model painting to the actual painting. So model comes first, 2,464, to the actual, 616, and then reduce that number. If we're lucky, if we did it right, it should reduce to a ratio of 4:1. Any questions on that?